So there was a movie a number of years ago, National Treasure, where Nicolas Cage goes and finds a secret message on the back of the Declaration of Independence. And that implied that there were some really intelligent people that had figured out how to encode that message and so on. What if there was a secret code built into math, built into numbers 1, 2, 3, 4? What if we discovered a secret code built into that? What would that imply? That would be fascinating, wouldn't it? Because that would imply that numbers themselves have a creator, and a very intelligent one, if we found a message built into numbers. And in fact, there is a code built into numbers. And it's absolutely amazing. It's mind-blowing. And this was discovered in really the 1980s. So this is relatively recent. People have been using numbers for thousands of years. But it wasn't until the 1980s that we discovered there is a code built into numbers. And I want to share that with you today because it's neat. This is something that I read about when I was young, and it just blew my mind, and I want to share it with you. Because we don't tend to often think about God creating numbers. We think about God creating the earth and the stars and the initial organisms on the earth. But God is also responsible for numbers. Not that he created them in the same way, because they're not physical, right? Numbers are abstract. They're conceptual. They exist in the mind. And yet God is responsible for numbers, and he has embedded in numbers an amazing code of unbelievable complexity and beauty. And I think it's going to be mind-blowing to you. It's really going to be mind-blowing. When I was a little kid, my mother would prepare these wonderful meals. She's a very good cook. But occasionally she'd prepare something I didn't like broccoli. Ooh. And the rule was you had to eat everything on your plate before you're dismissed, right? So occasionally, in rare moments of maturity, I would eat the broccoli first, get it out of the way, so that I could then enjoy the rest of the meal. You see what I'm saying? Well, in light of that, we're going to do some broccoli first. Okay, but stay with me because it's going to get really cool. Okay, so we're going to have to talk about sets. We're going to have to do a little bit of math here. And you'll see a set is just a collection of elements with a common defined property. And so when we're talking about sets of numbers, a set of numbers is just numbers that have something in common with each other. And you can define sets lots of different ways. In most sets, some numbers are included and other numbers are excluded. So we're all about sets today. And for example, consider the set of even numbers. So we got some numbers there. The set of even numbers would contain those ones, and it would exclude all the others, right? Because numbers that are divisible by 2, evenly divisible by 2. We could then consider the set of negative numbers. That's a different set. The set of negative numbers is a different set, and so it will have different numbers contained within it. It'll have those ones, and it will exclude the others. And those two sets are very easy because you can tell just by looking at the number whether or not it belongs to the set, can't you? Even, well, does it end in 0, 2, 4, 6, 8? Well, yeah, it belongs. Or is it a negative number? Well, you just look and see if there's a little negative sign in front of it. It's pretty easy. We're going to talk about a set that's a little bit more complex, where you can't tell just by looking at the number whether or not it belongs. You're going to have to think about it a little bit. You can figure whether the number belongs, but not just by looking at it. And the set we're going to talk about is called the Mandelbrot set. The Mandelbrot set, named after Benoit Mandelbrot, mathematician, very famous mathematician. And it's defined by this little formula that you see there. And C is the number that you're checking to see if it belongs to the Mandelbrot set. So that's what C is. And Z is another number that, in fact, there's many different Z's. That's why it has a little subscript N next to it. So there's a first Z, a second Z, a third Z, and fourth Z. You can think of them like a sequence of mailboxes. Each one's got a number in it. And if that Z sequence gets bigger and bigger and bigger, then that means C is not part of the Mandelbrot set. Whereas if the sequence of Z stays small, then C is part of the Mandelbrot set. That sounds very complicated. It's actually very simple. And we'll do a couple, and then you'll see how intuitive it is. It's really quite simple. So there's our little formula. Z, and by the way, Zn plus 1, that means that's the next mailbox. That's the next value of Z. And so it depends on the previous value and the number C. So we're going to ask, is the number 1 part of the Mandelbrot set? So that means C equals 1, because C is the number we're checking to see if it belongs to the Mandelbrot set. So we're going to plug that in. You can see we're plugging that in for C there. So Z squared plus 1 is the next value of Z. Now, the first value of Z is always 0. That's just part of the definition. So the first value is 0. We're going to plug that in. So you have 0 squared, which is 0. 0 times 0 is 0. Plus 1 is 1, yes. See, this isn't that hard. It really isn't. And so that's our new value of z. Now we're going to plug that back in like this. Now we have 1 squared, which is 1, plus 1 is 2. Very good. Even the Common Core folks are getting this. Okay. All right. We're going to put that back in. So we have now 2 squared, which is 4, plus 1 is 5. Okay. Put it back in. 5 squared is 25, plus 1 is 26. Put that back in. 26 squared. Oh, okay. Getting a little hard, isn't it? Okay. But we don't have to do any more. You can see what's happening. Is z staying small? No, it's getting big. It's getting very big very fast. So is the number 1 part of the Mandelbrot set? Answer is no. No, because the sequence of z has to stay small for c to be a member of the Mandelbrot set. So number 1 is not part of the Mandelbrot set. Let's check another one. Let's check -1. Is -1 part of the Mandelbrot set? So we're going to plug that in now. So we have z squared minus 1 is the new value of z, right? And we'll start z equals 0, and we'll plug that in. So now we have 0 squared, which is 0 minus 1 is -1, right? And we plug that back in. Now -1 squared, -1 times itself is +1. Minus 1 is 0. Well, that's kind of interesting. Put that back in. 0 squared. Wait a minute. This looks familiar. So it goes 0, -1, 0, -1. See that? Interesting. Does z stay small? Yeah. It never gets greater in absolute magnitude than 1. So is -1 part of the Mandelbrot set? Yes. Okay, you got it? It's easy. Tedious, but easy. Okay? So you can check any number. All you have to do is run it through that formula and take a look at what's happening with z. And sometimes it'll stay. If we tried it with 0, you'd find z is always 0. And so 0 is part of the Mandelbrot set as well. -1 is part of the Mandelbrot set. +1 is not. Okay, there's one more complication, and then it's going to get really cool. The Mandelbrot set also includes what are called complex and imaginary numbers. I hate the terminology because imaginary makes you think it doesn't exist. Well, they do exist. They do exist, but an imaginary number is a number that when you square it, you get a negative number. And that's a little hard for us to comprehend, right? Because and the sort of standard imaginary number is abbreviated by the lowercase I. And I squared, by definition, is -1. Okay? And then there are other imaginary numbers. And again, I hate the name because they do exist. And to add insult to injury, the numbers that are not imaginary are called real. But they all exist. It's just, a little bit hard for us to imagine. Imaginary numbers are not positive, right? Because a positive number squared is positive. And imaginary numbers are not negative because a negative number squared is positive. And imaginary numbers are not 0 because 0 squared is 0. So how do you have something that's not positive, not negative, and not 0? That's an imaginary number. And they do exist. It's just we're kind of uncomfortable with them because most people don't have a lot of experience with these numbers. It's kind of like when you're a little kid and you're first exposed to a negative number. And you say, well, how can something be less than nothing? That doesn't make any sense, right? Then you get a little bit older, you get a bank account, suddenly negative numbers make a lot of sense, right? Yeah. Well, it's the same way with the imaginary numbers. They do exist. It's just that most of us never really used them. How do we think about a number that's not positive, not negative, and not 0? Well, one way to think about it would be to consider a number line. So you have, on the number line, you have 0 there in the middle. You have positive numbers to the right of 0. You have negative numbers to the left of 0. Where are you going to put I? How about above 0, like that? Oh, that makes sense, right? It's not positive. It's not to the right of 0. It's not negative. It's not to the left of 0, but it's also not 0. It's off axis. And so you can think of the imaginary numbers as being on a different axis than the real numbers. And that is a very common way that mathematicians will express these numbers. And you can multiply the imaginary number I, which is it's the same distance from 0 as 1. Okay, and remember I squared is -1. And you can multiply that imaginary number by any real number and you get all these other imaginary numbers, you see. And so that generates that axis. You can also have complex numbers. They're called complex because they have a real part and an imaginary part. And they're off axis. And by convention, the real part we plot that's their x coordinate, and the imaginary part is their y coordinate. And so this is very useful in mathematics to talk about these complex numbers, because even though it's one number, you can represent it as a point on a plane. And that's kind of neat. So you can actually make some graphs and things that way. So those are complex numbers and imaginary numbers. They're off axis. And what we're going to do then is make a map of the Mandelbrot set, because it was kind of tedious going through that and checking that, but computers are great at doing tedious things. They can do math very quickly over and over. And what we'll do is we'll make a map of which points belong to the Mandelbrot set and which points don't. And that way, we won't have to run through that formula. We can just look at the map then and say, okay, that number, it does belong, and that number doesn't. So for example, numbers that do belong to the Mandelbrot set, we'll color those black. We checked -1, we found it did belong to the Mandelbrot set, right, because z remains small, right? And if we checked 0, we'd find it also belongs to the Mandelbrot set. If we checked other points, we'd find that all these points belong to the Mandelbrot set as well, just as examples, had we checked them. And then for points that do not belong to the Mandelbrot set, we'll color those red. Okay, and we checked 1. Remember, we found that 1, the sequence of z got really big. And so that means it's not part of the Mandelbrot set. And had we checked some of these other numbers, we'd find that they do not belong to the Mandelbrot set as well. Now, what's fascinating is that the shape here that emerges, this map of the Mandelbrot set, turns out to be something that's not simple at all. You might think, well, it'd be a circle or something. You can tell it's not, though, even right there. But as we have the computer check more and more points, we get a complete map of the Mandelbrot set. And the map that we get looks like this. It's surprisingly complicated and rather beautiful. And so, again, what we're having here is just a map of which points belong. Black means they belong to the Mandelbrot set. Color means they don't. And I shaded the colors so that if the sequence of z gets really big really fast, I made it kind of a dark color. So the points that are real far away from the Mandelbrot set. Whereas if z gets big, but it does so slowly, then I colored it like a brighter color, like yellow. So the points that don't belong are shaded. The points that do belong, those are all black. Just by convention, that's the way they do it. The colors are arbitrary. I could have picked any color I wanted to, except just by convention, the points that do belong are always colored black by convention. And so now I don't have to go through and run through that formula. The computer's done it for me. I can look and say, does 1/2 I belong to the Mandelbrot set? The answer is yes, it does. You can see it's black. Okay? And you can see the number 0 belongs. You can see the number 1 doesn't, and so on and so forth. And so I'm going to remove that grid, because what's interesting is this shape. It turns out this map of which points belong to the Mandelbrot set turns out to be just wonderful. It's remarkably complex and beautiful and surprising. No one was expecting this to exist in the world of math, but there it is. And it is a fascinating shape. You have sort of, there's sort of 3 types of shapes that stand out, at least to my eyes. There's the largest shape, which is called a cardioid. That's kind of that heart-shaped feature. And then growing off of that are a bunch of circles, and they are perfect circles. And then growing off of that are other circles and these little tendrils that kind of, like little lightning bolts that grow away from it. Now, the main shape, the cardioid, is what you get when you take one circle and you roll it around another circle, keeping your pencil on one point on the main circle. That's a cardioid, and you can see that is the exact shape of the main part of the Mandelbrot set. Nobody was expecting that, but there it is. And then all the other shapes are either perfect circles or these little lightning bolt wisps that kind of stem away from it. Now, if we can actually zoom in, thanks to the power of computing technology, we can zoom in on various sections of the Mandelbrot set and see what it looks like. And so we find, for example, if we zoom in on this upper tendril there, you can see that it branches off. That circle has another circle on top of it, which has another circle on top of it, and it grows into this little sort of little tree there, where it has 2 branches on it and a trunk, so 3 total. So it branches off into 3. You see that? 3 branches. And if you look at the next one to the left, it branches off into 5. Can you count that? Including the trunk, including the stem. 1, 2, 3, 4, 5. The next one is 7, 9, 11, 13, 15, 17. All of the odd numbers. Isn't that interesting? Each one has 2 more tendrils than the previous one. That's interesting. Nobody was expecting that. And if we go to the right side, we find all the numbers, even and odds. And so 3, 4, 5, 6, 7, 8. Interesting, all the way down to infinity. And on the left side, we have all the odds, all the way down to odd infinity, apparently. Interesting. And so apparently the Mandelbrot set somehow knows how to count. That's kind of fascinating. And all we're doing is looking at a map of which points belong, and yet it turns out these structures are remarkable. Not only that, but if you take 3 and the 5, and of course you add those together, you get 8, and lo and behold, that is exactly how many the one in between them has. Isn't that interesting? If you count the tendrils there, I know they're kind of small, but it's got 8 tendrils. And that is true for all of them. If you go in between any of them, the number of tendrils in between is the sum of the two surrounding them. Isn't that fascinating? So not only does the Mandelbrot set know how to count, it knows how to add. Isn't that interesting? Nobody was expecting that. Fascinating. So all that built into a map of which points belong to that simple little formula, z squared plus c. One of the most remarkable things about the Mandelbrot set, though, concerns this little spike that we have growing off the left of the set there. And you'll notice that that spike has a little black bump on the end of it. What could that be? Well, let's zoom in on that and see what that looks like, that little bump. Turns out it's another Mandelbrot set. Isn't that fascinating? And it's almost identical to the original. It's got the main cardioid, the circles growing off of it. The only difference is it's got extra spikes growing off of it. We zoomed in on a spike, and the baby version had extra spikes growing off of it. And if you'll notice, one of those spikes, the one at the very end, has a little black spot on it. What could that be? Well, let's zoom in on that. Turns out it's another one. Isn't that interesting? And it's again, identical to the original, except it's got even more spikes growing off of it because we zoomed in on a spike of a spike, and it's got extra spikes growing off of it. And it's got a little thing there too. What could that possibly be? Well, it's another one, and so on and so forth. This continues infinitely. Interesting. So the Mandelbrot set has an infinite number of baby Mandelbrot sets growing off of that spike. And each one of those has a spike, has a Mandelbrot growing off of it, and so on. All of that, just a tiny little section of the original. Look how much we've zoomed in there. It's quite amazing. Isn't that fascinating? And nobody was expecting that. Who knew that when you plotted a map of which numbers belong to z squared plus c, you would get this amazing structure? And it's not just the overall shape that repeats infinitely. If you zoom in on any part of the Mandelbrot set, it goes forever. And it's quite fascinating to see this. You might think, well, it's going to end at some point. I'm just going to keep zooming in until it stops, but it just doesn't stop. No matter what you zoom in on, it just keeps fragmenting and keeps fragmenting smaller and smaller scales. It's not like the physical universe. The physical universe eventually get down to atoms. There's no atoms here. This is made of math, okay? And so it goes on literally forever. Isn't that fascinating? And of course, well, we'd be here all day if we zoomed in on the whole thing, right? Because we would literally take forever, but it's quite fascinating. One of the interesting regions in which we can zoom in on the Mandelbrot set is the valley between the main cardioid and the first disc, that big circle that's growing off to the left of the cardioid. That valley, if we zoom in on it, either the top or the bottom, they're symmetric. If we zoom in on that, it's called the Valley of the Seahorses. And you can see it looks like seahorses off to the right. They're upside down. And double spirals off to the left. So we can zoom in on those shapes and see what they look like. So let's zoom in on one of those seahorses and see what that looks like here. And by the way, the colors are arbitrary, so we'll change those every now and then just to keep things interesting. But bright colors mean close to the Mandelbrot set, but not quite on it. Dark colors mean far away from the Mandelbrot set, and black means it's on the Mandelbrot set. So we zoom in on one of these seahorses. Now, keep in mind, all you're looking at is the plot of an equation. It's the equation z squared plus c, and which points belong to that. And what you have, given that seahorse is very brightly colored, that means that those points are very close to being on the Mandelbrot set, which means there must be actually a very thin black thread that extends away from that circle that wiggles around it's incredibly wiggly. In fact, it's infinitely wiggly, if that makes any sense. It's as wiggly as is possible for 2 dimensions. And it wiggles around, and what you're seeing there is the black is too thin for the computer to plot it. But the fact that you're seeing bright blue there indicates that those points are very close to being on the Mandelbrot set. So that seahorse is made of an infinitely wiggly thread, or multiple threads, that wrap around and form kind of a spiderweb structure there in the middle. Quite beautiful, and they form a beautiful spiral up near the top. Isn't that stunning? And who would have expected that such beauty would be built into a map of the Mandelbrot set? It's absolutely fascinating. So let's zoom in a little bit more and see what that spiderweb structure looks like. And it looks like that. And I found from experience you can zoom in on the center of that till your heart's content and nothing changes. It goes forever. It's an infinite spiderweb. And so what we'll do is we'll go off axis. We'll look at one of the strands of the spiderweb, see what it's made of. And we find the spiderweb strand is made of more spiderweb strands, interestingly, and spirals as well. Quite lovely, really, very beautiful. We zoom in on one of those. We find an interesting structure there. You find that there's kind of two central hubs, one on the top, one on the bottom, right? You see those where there's bright yellow in this illustration. And then it goes to 4 in the middle there. You can see there's 4. And then when we zoom in, you'll see it'll go to 8, 16, 32, 64. It's all the powers of 2. So not only does the Mandelbrot set know how to count, know how to add, it knows how to do powers of 2, interestingly. So let's zoom in on this central, that central 4 little square structure there. And you find that in the middle is, well, that's interesting. It goes from 4 to 8 to 16, and then right in the middle is, of course, another baby version of the Mandelbrot set. Isn't that amazing? And we've zoomed in, I don't know how many times, but this is a tiny little structure built into the original. And you can see that it, too, has a little baby Mandelbrot set on its spike, just like the original did. But now it's surrounded by all this extra stuff, all this extra kind of spiderweb type structure, because we zoomed in on a spiderweb, and the baby version apparently inherits the properties of the section of the parent that it grows off of. So quite stunning. And take a look at how small this is compared to the original when we zoom back out. It's quite amazing. And that just gives you a little window into the mind of God. Because if you think about it, God is responsible for numbers. God is the reason that numbers exist, because they exist in his mind. And we'll talk about this more later. But what this is it's giving you a little window into how God thinks. And so when you zoom in on these things and you think, wow, God is infinite, this is just a little taste of what infinity is like. Just a taste of it. We can't really experience infinity in its fullness. We can get a glimpse of it. Well, let's go back to the Valley of the Seahorses. They're on the right side. And this time we'll go off to the left in what they call the Valley of the Double Spirals. And this is my favorite section of the Mandelbrot set. It's strikingly beautiful. It reminds me of spiral galaxies, actually, in terms of the way these structures are. It is a double spiral meaning that there are 2 strands that wrap around each other. If you were to take a look at this strand is the same as that strand, but not that one, right? Because if you follow it around, you can see, yeah, there's 2 independent strands that wrap around each other. So it's a double spiral. And it's strikingly beautiful, I think. So again, you're just seeing a map of which points belong. There must be a very thin thread of points that belong to the Mandelbrot set that wiggles around and forms this beautiful, intricate spiral structure, all built into numbers. It's been there since creation, but it was only in the 1980s that computers were fast enough to be able to plot these things in a reasonable amount of time. And it's even easier today because computers are faster. Again, I found if you zoom in on the center of that double spiral, you can do that forever. It continues infinitely. It spirals forever, literally. Infinitely smaller. So let's go off axis and zoom in on one of these strands. And quite lovely. We find that you find more double spirals off to the side, up on the top, for example. There's some of those spiderweb structures, and there's a structure, I call it a bow tie. It looks like a little bow tie there in the middle, where you have 2 double spirals that intersect in the middle. And I find these to be stunningly beautiful. So who could have guessed that this is all built into numbers? Been waiting for us to discover it for 6,000 years. And so again, you have the 2 double spirals, and then in the middle it goes to 4, 8, 16, 32. And of course, when you zoom in on the middle there, you find, lo and behold, another baby Mandelbrot set. Do you get the feeling that God really likes that shape? Because it just occurs everywhere. There's an infinite number of them. And again, it's identical to the original, except, of course, it's rotated around. If you notice, this one's backwards compared to the original because we zoomed in on a spiral, and so it got rotated around. And also, we have double spirals growing off of it. And you can see the 8 primary ones there, and then there's 16 inside that and 32 inside that. All the powers of 2, all the way up to infinity, amazingly. And of course, it's got a little baby on its spike as well, as they all do. So not only does the Mandelbrot contain an infinite number of copies of itself, but each of those copies has an infinite number of copies as well. Because if you think about it, this also has a Valley of Seahorses, doesn't it? I could zoom in on it, and so on. So it just gives you a little glimpse into the infinite mind of God. One other valley that's interesting to zoom in on is the one on the where the cardioid, the main cusp of the cardioid, and we call this the Valley of the Elephants, and you'll see why when we zoom in here. Mathematicians like to give names to these different sections, and Valley of the Elephants. It looks like elephants marching one after the next, doesn't it? And their mirror image as if they're hanging from the ceiling, going along that way. But we'll go to the bottom row. It reminded me of elephants in a circus. They're like standing on a ball, right? Because each one of those circles has one elephant growing off of it, doesn't it? And there's an infinite number of them. They go all the way to infinity into that cusp. So each circle, one elephant balancing on it, as if a circus elephant. We can zoom in on the trunk of one of these elephants, and you can see the trunk wraps infinitely, actually. It wraps around itself, and it's quite lovely. And again, you can zoom in on the center of that forever. It continues infinitely, gets smaller and smaller to an infinitesimal scale. So we'll go off axis and look at the structure on the side. We find, again, it looks like kind of elephant-like structures. There's some bow ties there, too, if we zoom in on one of those. There's one of those bow tie shapes, but now they're single spirals. Yeah, this is an Alienware. It's not supposed to do that. Oh, okay, we're all right. Okay. The reason I got this is so I could do this presentation. All right. No, it's working great. So again, you have that bow tie structure, but it's single spirals rather than double. And if you zoom in on the center, it goes from 2. It's doing it again. That's weird. Let me back up a little bit. Yeah, I don't know why it's not animating. I'm sorry about that. But anyway, that's what you get to when you get to the center. And you get this beautiful baby Mandelbrot that's surrounded by all this lovely structure. Isn't that stunning? And all built into this shape. It's just a plot of which numbers belong to the Mandelbrot set, z squared plus c. Seems very simple, and yet God has built incredible beauty into math. That's remarkable. All that, just a map of that formula, which numbers c remain, for which the sequence of z remains small. That's all there is to it. And so that got me thinking, what happens if we explore other formulas? I mean, this shape itself, you understand, you could spend the rest of your life studying this and you would only scratch the surface because it's infinitely complex. And it's just one equation. That tells us something about the mind of God. I found that if I change c, if I make it like half c or 2c or minus c, all it does is change the shape. It'll flip it around or make it bigger or smaller. You still get the Mandelbrot set. What if I change z squared, though, to something else? What if I try z cubed? What do I get? Well, it turns out you get a different shape. Now we've got another object to study. And is it complex like the Mandelbrot? Well, let's find out. Let's take a look at this shape. They call this a multibrot because it's a multiple of the Mandelbrot set. And so this is z cubed plus c. Those are the points in black, are the points that belong to that formula when you run it through that iteration. And you notice what's happened here. Everything's gone up by 1. Because remember, the Mandelbrot set had the cardioid, which has one cusp, and the rest of it's round. Now the main shape has 2 cusps, one on the left, one on the right. And the Mandelbrot set had perfect circles growing on them, which have no cusps, and now they have cardioids growing off of them, which have 1 cusp. Everything's gone up by 1. The main shape there, with the 2 lobes, that's called a nephroid, and that's what happens when you take a circle that's half the size of the other one and you roll it around like that. That's a nephroid. And you can see that is exactly the shape that is produced when we have z cubed plus c. Why? Nobody knows. I'm sure there's a reason, a very good mathematical reason. We have yet to discover it. Because our ability to think God's thoughts after him is quite limited. And in fact, you can see how the Mandelbrot changes into the multibrot. What I did was I ran it through the formula and I changed it gradually. I changed it from z squared to z 2.1, 2.2, 2.3, all the way up to z cubed. And so you can see what happens. You can see how everything gets kind of doubled. Some things get up by a factor of 4, like the little baby Mandelbrot there. It first gets split into 2, and then it's joined by a twin, so it actually ends up being 4. But most things are doubled. And so that's kind of interesting. Now, the one thing that doesn't really change very much, in fact, let me back up and do that again. The one thing that doesn't change very much is the Valley of the Elephants, right? Everything else gets kind of moved around, but this valley looks like it stays pretty constant. So I thought, what would happen then if we zoomed in? Does this shape also have a Valley of the Elephants? Well, let's find out. Let's zoom in on it. Let's see what we find. Lo and behold, we find elephants. How about that? But you notice before we had circles and we had one elephant growing off of each circle. Now we have cardioids, and there's 2 elephants growing off of each one. So the elephants have doubled. Before we had an infinite number of elephants, and now we have twice that many. Simmer on that for a while. So there you go. Each cardioid now has 2 elephants growing off of it. Isn't that amazing? So, and we can zoom in on the trunk of one of these elephants and see what happens. You're going to get the bow tie structures, you think? Let's find out. The bow ties have become 3. They've gained a spiral, right? Instead of just 2 spirals intersecting, they have 3 now. And lo and behold, what do you find in the center there? First of all, it goes from 3 to 9 to 27 and so on. It's all the powers of 3 now instead of the powers of 2. And you zoom in on the center one, and sure enough, you get the basic shape. You get the nephroid with the cardioids growing off of it. So it's a fractal as well. Anything like this that repeats infinitely is called a fractal. A fractal is something where the overall shape is repeated on smaller and smaller scales. And so we've just explored 2 different fractals now. Kind of amazing. So that's what happens when you have z cubed plus c. What happens if you do z to the 4th? Well, you get that. Everything goes up when you have one other cusp now, you see. And z to the 5th. Z to the 5th gives you a 4, if I back up a second, z to the 4th gives you kind of a 3-fold symmetry. Z to the 5th gives you a 4-fold symmetry. Z to the 6th gives you a 5-fold symmetry. And so it occurred to me if I made z to the 7th, I could get snowflakes. 6-fold symmetry. And when you zoom in on this, do you get snowflakes? Absolutely. You zoom in on portions of it, you get these beautiful snowflake structures. So it's also fractal. Isn't that fascinating? I also tried negative powers. What happens when you try z to the negative 2? Now, the interesting thing about this, remember, black are points that do belong, and colored are points that don't. And so what happens is now almost the entire universe belongs. The black is outside now. It's inverted because it's a negative power, you see. And so now most of the universe belongs to that set. It's these points in the middle that don't. And if I zoom in on these are fascinating because it produces kind of like a pebble-like structure that I think are remarkably beautiful. Isn't that interesting? And if we zoom in on that, what do we find? Pebbles upon pebbles of stunning beauty. Does it repeat infinitely? Well, let's zoom in here. Absolutely. It goes on forever and ever and ever with the pebbles of smaller and smaller scales. It's not like the physical universe where you get down to atoms and then they're just spheres. Here, it goes on literally forever. You could zoom in on that for the rest of your life. So that's z to the negative 2. What happens if you do z to the negative 3? You get that. Z to the negative 4, you get that. Z to the negative 5. Again, there's a progression there. And so there's another type of snowflake that you can get. So isn't that fascinating? All we're doing is looking at maps of which points belong to that little formula, and changing the formula doesn't just gives you new shapes. So what does all this mean? I mean, are we just looking at pretty shapes here? What does all it mean? Well, my question is, what causes this beauty in fractals? Where does it come from? How do we account for it? How do we make sense of it? What causes the complexity in fractals? The fact that you can zoom in on them, they have these mathematical properties, they continue infinitely. How do we make sense of that? Well, first of all, what causes the beauty in fractals? Is it the man-made color scheme? I picked the colors. I think they're pretty. But the fact is, even if you take away the color, the shape is still beautiful, even in grayscale. Okay, and I didn't pick the shape. Nobody did. No human did. So it's not the man-made color scheme. That's not it. I think that adds to it, the way a little bit of salt will bring out the flavor of your food. But it's not creating the beauty, not at all. Did the computer create the beauty? Well, we saw the computer plot this, but the fact is, the computer just did quickly what you could do manually. We did the first 2 points manually. Remember, we did -1 and -1, and we found whether or not they belong. So no, this shape is built into numbers. The computer just helped us to reveal it quickly. You could theoretically do this all by hand. It would just take forever. And so this didn't create the beauty any more than a microscope creates the complexity of a microbe. No, it just allows us to see it. Did people make this? Well, we came up with the formula, but what we've seen is that the formula doesn't really matter too much. You can change the formula, you still get these wonderful shapes. And frankly, no human being sat down and said, okay, I think I'm going to make this shape where it's like, a cardioid here, and then I'm going to put some circles on it, and I think I'll draw an infinite number of, human beings can't draw an infinite number of things. Human beings did not create this. We can't create infinite. We discovered it. We did not create it. And so it seems to me the beauty is built into math. The beauty of fractals is built into math somehow. Well, what causes the complexity in fractals? The fact that they repeat and have these mathematical properties, what accounts for that? Did the computer create it? Obviously not. The computer simply reveals it. You could do these, you could plot these manually, theoretically. Did human beings create it? We can't create things that are infinitely complex. Think about it. Man-made machines, you get down to some level and then they're very crude and simple. We can't do that. We can't create an infinite number of minis built into the original. We could create several, but not an infinite number. That's beyond us. It's not something that human beings created. Did the formula create it? Well, the formula doesn't matter too much. The formula reveals it. The formula defines what points belong and what not. But it's not like people picked a formula to give that shape. People picked the formula and were surprised by that shape. Very surprised. So it seems to me the complexity is somehow built into math. Interesting. Here we have a shape that's been built into numbers, built into math. What is math? Aside from that subject that's really hard in school, math is the study of the relationship between numbers. That's really how you could define it. It's how numbers relate to each other. Well, what are numbers then? And it's funny, some of these things that we use every day and we don't think about how are they defined? How would you define a number? I looked through several dictionaries, and it's hard to get an exact definition of that. The best I could find is a dictionary that said numbers are a concept of quantity. I think that's the best definition I've been able to see. And so if you have, 2 oranges and 2 rocks and 2 people and 2 galaxies, what do they all have in common? Two-ness. You abstract away the physical thing, and what you're left with is a concept, the concept of quantity. That's what numbers are. They are a concept. Now, the thing about concepts is they exist in the mind. Concepts are something you think. Numbers are something you think. They are abstract in nature, not physical. You cannot stub your toe on the number 2. You can stub your toe on something physical that maybe there's 2 of them, but you can't stub your toe on two-ness, right? You just can't do that because it's not physical. They exist in the mind. You can't trip over a law of mathematics or pull one out of the refrigerator or accidentally swallow one. They're non-physical. They are abstract. They exist in the mind. You say, well, I don't know, that number 3 is physical, right? I see it there on the screen. That's the number 3. Is it the number 3, really? Because if so, then I just destroyed the number 3. Oh, wait a minute. That wasn't actually 3, right? Because it's not like children will now have to count 1, 2, 4, because there's no more 3. I just destroyed it. No. We get it. That was a representation of 3, right? That was a numeral. Written numerals are not numbers. They are representations of numbers, and they can be written different ways. I could write 3 with 3 vertical lines, right, like they do in Roman numerals, or I could use, Arabic or whatever. Those are just representations of numbers. But the concept of 3-ness is not something you can write down because it's mental. It exists in the mind. Laws of math are conceptual. They exist in the mind. So these laws that we have, the multiplication, the commutative property of multiplication or distributive property and so on, these are conceptual. They exist in the mind. Now, they're very effective in how we get along in the universe. They help us, but they exist in the mind. So where do laws of math come from then? There's an interesting question. We use these laws of math, the Pythagorean theorem and so on. We use these laws. Where do they come from? Did laws of math evolve? Well, we've seen a shape that's incredibly complex and beautiful. And in the natural world, in the physical world, when we find something like that, an organism that's incredibly complex and appears well-designed, these secularists say, well, that evolved, right? It used to be very simple, but then it gradually became more complex over time. Is that going to work for math? It doesn't really work for biology, but was it like the Pythagorean theorem didn't used to be true, but it gradually Well, no. The 2 plus 2 used to equal 3, but then it slowly changed, and now it equals 4. And no, laws of math don't evolve, do they? They've always been exactly as they are now. That we discovered them over time, but it's not like 2 plus 2 ever at one point in time equaled something other than 4. They've always been the way they are now. There's no such thing as evolutionary math. Everybody does math like a creationist. Isn't that interesting? Whether they profess it or not. Were they created by people? Oh, well, Pythagoras created the Pythagorean theorem. Really? Did triangles not add up that way before Pythagoras? Oh, he just discovered it. He wasn't the first, by the way, but he was able to demonstrate that. It's very clever. They're not created by people. Laws of math worked perfectly well before people were around to describe them. The way the planets orbit the sun, they obey what are called Kepler's laws, and those are mathematical. The period of a planet squared is equal to its distance from the sun cubed in the appropriate units. And so, now, was that the case before people? Yeah. A few days before people. Because planets are made on day 4, people are made on day 6. Yeah, but my point is the planets orbited perfectly fine before people came along, and they orbited according to laws of mathematics. And even the secularists would concede that. So my point is people did not create laws of math because math worked perfectly well before people were around to describe it. Did they come from the universe? That's a common belief, especially among secularists, is that, well, the universe behaves a certain way, and we call that math. But I think that is utterly indefensible because there are things in mathematics that have no analogy in the physical universe. For example, the number of dimensions. The physical universe has 3 dimensions of space, 1 of time. In math, you can have any number of dimensions. You can have 16 dimensions if you like. There's a thing called Hilbert space that has infinite number of dimensions. That has no correspondence to anything in the physical universe. And yet, it makes sense. There's rationality to it. So my point is math goes beyond the physical universe. The physical universe doesn't get infinitely small. You get down to the level of atoms and then in quarks, and then there's kind of a quantum fuzziness there. But these shapes go on forever. So math didn't come from the universe. Now, it's interesting that math can describe the universe, but that's a separate question. That's a separate puzzle for secularists. Obviously, math doesn't come from the universe because it goes beyond the universe. You can do things in math you can't do in the physical universe. You can have infinities in math. You can't have those in the physical universe in terms of infinite lengths and things like that. Seems to me that laws of math stem from the mind of God. In the Christian worldview, I can make sense of numbers. Numbers are what God thinks of quantities, which is how they exist before people, you see. And laws of math, they stem from the mind of God. Mathematics is the way God thinks about numbers. That's what math is. And if you want to study it right, you need to know something about God. Laws of mathematics are conceptual. They exist in a mind. They're universal, meaning they apply everywhere, right? It's not like 2 plus 2 equals 4. Well, sure, here on Earth, but on the moon it might equal 5 or 7. No, they apply everywhere, don't they? They're invariant, meaning they don't change with time. 2 plus 2 equals 4 today and tomorrow and last week and next Thursday. It doesn't matter, right? And we all assume that. And they're exceptionless. It's not like 2 plus 2 equals 4 most of the time, but every now and then it's 7. No, it doesn't work that way, does it? And if you think about it, these properties of laws of mathematics make sense in light of the fact that laws of mathematics stem from the mind of God. Because God's thoughts are conceptual, because all thoughts are conceptual. So naturally, laws of mathematics would be conceptual. They would be universal because God is omnipresent. He is sovereign over all creation. He's everywhere. And so his thinking will govern correct thinking everywhere in the universe. God does not change with time. Therefore, laws of mathematics will not change with time. The way God thinks about numbers today is the way he thought about numbers yesterday and the way he will always think about numbers because God does not change. And laws of mathematics have no exceptions because God is sovereign over everything. And so they cannot defy their creator that way. They can't. And so I would argue that the Christian worldview can make sense of fractals. We can make sense that mathematics has beauty built into it and complexity built into it. We can make sense of laws of mathematics and the reason that they are universal and invariant and exceptionless. That all stems from the nature of God. The Christian worldview can account for this. The naturalist has a problem. Somebody who believes that nature's all that there is. He's got a problem because on the one hand, laws of mathematics are conceptual. They exist in the mind. You can't stub your toe on a law of math. Accidentally swallow one. You can't do that. They're non-physical. On the other hand, laws of mathematics existed before people. So on the one hand, they're a product of the mind. On the other hand, they existed before human minds. But you see, in the secular view, human minds are the first, unless there's aliens or something out there, right? And even then, the mathematics would exist before them, because the universe is governed by mathematical laws. And so the naturalist has a real problem on his hands. He's got to account for laws of math that are conceptual, and yet he doesn't have a mind beyond people to appeal to. That's a problem. But in the Christian worldview, it makes perfect sense, because we understand there's a mind beyond people, the mind of God, that is sovereign over the entire universe. I can make sense of laws of mathematics and their properties. The secularists can't. There are also physical fractals. This is kind of interesting. Now, the perfect fractals we've discussed that repeat infinitely, those are only found in mathematics. Mathematics goes on forever. The physical world, you zoom in so much and you get to the level of atoms and things stop being fractal. But nonetheless, the physical world contains things that are approximate fractals. They repeat many times, just not infinitely times. Okay? And so let's take a look at some of these. Fractals in the physical world. One that you're very familiar with in Nebraska, the snowflake. Yeah. And these little gems from heaven that we get angry at and shovel them off our car, but they're quite stunningly beautiful when you take a look at them on the microscopic scale. They are fractal in the sense that that same basic pattern repeats. Maybe not exactly, but you can zoom in, you still get the six-fold symmetry due to the nature of the water molecule and so on. So snow has a fractal shape to it. It really does. That's stuff that grows on your windows. I always thought this was amazing when I was a kid, and frankly, I still think it's amazing. These beautiful patterns that will form on your window when the humidity's right and the temperature's right. It's a fractal pattern. You zoom in on it, it branches and it branches and it branches and so on. And so and it's quite lovely. And ferns are fractal because you have a stem and it has growing off the side stems, which have growing off the sides of those stems, which have growing off the side, and so on. And it repeats on smaller and smaller scales. The overall fern looks similar to any section of it. That is a fractal. I even found fractal broccoli, so I guess broccoli is good for something after all. So there you go. It's called Romanesco broccoli. And you zoom in on it, you see it's these cone shapes, but the cones are made of smaller cones, which are made of smaller cones, which are made of smaller cones. And so that is a fractal, interestingly. So the way coastlines are, the way they divide, the way the rivers branch and branch into branches and branch into branches of branches, the way the coastline is fractal. Mountaintops, the way they split is fractal, the way they branch and branch into branches and so on. Clouds have a fractal nature to them. Am I looking at the entire sky? Am I zoomed in on one very small part of the sky? Hard to tell, because the same kind of patterns repeat on smaller and smaller scales. The way lightning branches is fractal, because you have the main bolt and it branches into smaller bolts, which branch into smaller bolts, and so on. And so lightning does have that fractal property to it. And you can actually see it, I think this is wonderful, in time-lapse or slow motion, where you can see it, and isn't that amazing, until the leader finally connects, and then most of the current goes down that path. But the way it branches is fractal. So here's my question then. Why do fractals occur both in math and in the physical world? Right? Because we got mathematical fractals that have been built into math since creation, only discovered in the 1980s. And then we've got these physical fractals that people have known about for a long time that are approximate fractals, lightning bolts and mountain chains and so on. Why do they exist together? I mean, that's a mathematical plot. That doesn't exist physically anywhere in the world. That's a Mandelbrot. It's z to the 7th plus c. And yet, that does exist in the physical world. We've got a lot of them outside right now. This is part of the Mandelbrot set. It's one of those tendril branches, and yet that is a lightning bolt that exists physically. So one is math. It's not made of atoms. It exists in the mind. The other is physical. It's made of atoms. It exists in the physical universe. We have this shape. That's actually a mathematical graph. It's called a Barnsley fern. And what it is each leaf of the fern is the entire fern. I'll show you this. Watch this. The entire fern is one of its leaves. See that? That's just cool. Let's do that again. You can do it infinitely, right? So that's a Barnsley fern. And yet there are real ferns that approximate that. Now, they don't go on forever, right? Because at some point you get down to atoms, and even before that, the fractal breaks down. But they're similar. One exists only in the conceptual world of math, the other physical. You got that shape? That's a mathematical plot, and yet that grows on your windows. You've got this shape, that's a mathematical plot. It does not exist in the physical world, whereas this, unfortunately, does. You got this shape, that's part of the Mandelbrot set, part of the Valley of the Double Spirals. You can't see that anywhere in the physical universe, or stub your toe on it, or touch it, but this you can see in your telescope. Not too far off the Big Dipper, the handle of the Big Dipper. Yeah, I've seen it many times. Interesting. So why do fractals occur both in math and the physical world? Now, one answer to this, and I think it's a reasonable answer, it's just insufficient, is that the physical universe obeys mathematical laws. The universe obeys math. So it stands to reason that if fractals can occur in math, they could also occur in the physical world, since the physical world obeys math. I agree, that's good. But then, of course, I'm going to have to ask, why does the physical universe obey mathematical laws? Well, we just take that for granted. Yeah, we do. But why is that? Why is it that the universe, which is physical, made up of material, obeys laws that are conceptual, that exist in the mind? How is that possible? Well, in the Christian worldview, it makes sense, because mathematics is a reflection of the way God thinks, and whose mind is in control of the universe? God's. And so naturally, mathematics will be reflected in the way the physical universe behaves. It makes sense. The universe is upheld by the mind of God. God upholds all things by the word of his power. And so the way God controls the universe will be mathematical because God thinks mathematically. So yes, the universe will obey math. But I would argue that the secular worldview can't answer that.
Human behavior.
What's that?
Human behavior.
Human behavior?
How does it fit this? Does it? Can it? Part of the mind of God.
Well, God does control us, but he's given us freedom of choice. So we're free to sin, right? And the physical universe doesn't have that option. The physical universe has no option but to obey God. But it is fallen. That's true. But nonetheless, it still obeys him perfectly. God cursed it, and it was cursed according to the way that he intended. So yeah, I think we can make sense of human behavior in the Christian worldview, because in our worldview, the physical universe is not the whole ball of wax. There's more to reality than the physical universe. There's the spiritual world as well. And in terms of the way our spirit interacts with the physical world, it's called the mind-body problem. That's an interesting issue. I'm not going to get into that, except to say that in the Christian worldview, we can make sense of the fact that we have a mind. There's something beyond, there's something more to us than simply our atoms. Isn't that right? We have a spirit. And so in the Christian worldview, the physical universe is not the only thing. There's more to reality than the physical universe. There's God as well. But I'm going to argue that the secular worldview can't make sense of why the physical universe obeys mathematical laws. Or frankly, why the laws of mathematics have the properties that they do. Why is it that laws of math are universal? And frankly, how could you possibly know that? How do you know that laws of mathematics work in the Andromeda Galaxy? You've never been there, and yet we all assume that. Every astronomer I've ever met assumes that the laws of math work the same in the distant universe as it does here. And I would argue, yeah, it makes sense in the Christian worldview, because God's sovereign over the Andromeda Galaxy just as he's sovereign over the earth. And so that makes sense. Why is the universe compelled to obey math? Well, in the Christian worldview, it's because the universe is controlled by the mind of God, and God thinks mathematically. Yeah. But in the secular worldview, there's no explanation for this. You don't believe me? Dr. Eugene Wigner, who was a brilliant physicist, I believe he was a Nobel Prize winner, wrote a wonderful article entitled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences," in which he attempts to answer this question: why is it that the physical universe obeys these conceptual mathematical laws? Why is that? And it's a wonderful read. And by the way, I'm not making fun of this guy. He is brilliant. He really is. But my point is, he's not thinking as a Christian. And so what does he come up with? He says, well, it's difficult to avoid the impression that a miracle confronts us here, or the two miracles of the existence of laws of nature and the human mind's capacity to divine them. He says it's weird enough, it's miraculous enough that there are laws of nature that are expressed mathematically. And what's even more strange is that the human mind, which I suppose in his view is just a chemical accident, has the ability to discover those laws of nature. And they're congenial to our understanding. And some of them are very simple, like F equals ma. Well, that's nice and convenient, isn't it? I mean, God couldn't have made that simpler. E equals mc squared. Why squared rather than 2.73651? Squared. It's perfect too. It's as if the universe was made to be understood, at least partly. And he says it's difficult to avoid the impression that two miracles confront us here. The existence of laws of nature, which are mathematical in nature, and the human mind's, the ability of the human mind to extract some of those, to discover those. So what is his conclusion? What does he come up with? Here's his conclusion. The miracle of the appropriateness of the language of mathematics for the formulation of laws of physics is a wonderful gift which we neither understand nor deserve. Isn't that interesting? And I have great respect for him for admitting that in the secular worldview, he cannot account for why there are laws of mathematics, why they exist, and why the universe obeys them, and frankly, why the human mind is able to extract them and understand them. So, and I agree that there is no solution in the secular worldview. But in the Christian worldview, it makes perfect sense, doesn't it? Because we have a mind that is sovereign over all nature. It's sovereign over concepts like mathematics, and it's sovereign over the physical universe as well. And that's the mind of God. So I can account for the success of science in my worldview. I can account for fractals. That's not to say that I understand everything about them. I don't. They're infinite. But I have a worldview in which they can exist, and it makes sense that we can have things like fractals. So we've seen that beauty, tremendous beauty of infinite complexity is built into numbers. Amazing. Revealed when we plot them by these little formulas. Numbers, we've seen, are abstract conceptions of quantity. They exist in the mind. And so when we study these fractals, we're studying the way God thinks, or at least one aspect of the way God thinks. And we get these little glimpses into infinity. You're like, wow, God's mind is awesome. Concepts require a mind. And so when you're studying numbers, you're studying the way somebody thinks about something. And of course, we've seen that numbers exist before people, and therefore they're a reflection of the way God thinks. And not always the way we think. We can make mistakes in math, God cannot. The secular worldview cannot account for the existence and properties of numbers or mathematical truths, and we've seen how that fleshes out, and we've seen that admitted by a brilliant physicist. Numbers existed before people, yet they are conceptions, meaning they require a mind, and that implies that there's a mind before people. Laws of mathematics are universal, same everywhere. Invariant, they don't change with time. They're abstract, they're not physical, and all those things make sense if laws of mathematics are the way God thinks about numbers. And so we can explain that because God himself is omnipresent and he doesn't change with time. And he is, of course, his thinking is abstract. He himself is non-material. So, of course, we can have non-material things that exist in the Christian worldview. The physical world contains fractals as well, at least approximate fractals, and we can make sense of that. But the secular worldview can't. Because why the physical universe obeys mathematical laws, according to Dr. Wigner, it's a miracle that we neither understand nor deserve. But in the Christian worldview, we can make sense of that because the universe is controlled by the mind of God. The Bible says, God himself says in Isaiah, I will accomplish all my good pleasure. God upholds all things by the word of his power. And so he does control the universe. And so, again, check us out, Biblical Science Institute. Pick up some of the resources if you can. And I'll see you back this afternoon for the Q&A session. Thank you very much.